Hey guys, this is Mrs. Ross. I am here to go over sections 4.3 and a little bit of 4.4. This morning I did have our class and I forgot to record it. So instead you get a recording of me going over these two sections. So I wanted to talk to you today about 4.3 and 4.4. Make sure you've watched 4.1 and 4.2. If you remember, we're in chapter 4. And we're learning all about triangles. So we are learning all the different ways that we can classify triangles, and now we're really focusing on congruence of triangles. So remember, congruence is kind of that fancy geometry term that just means equal, right? And these next few sections, we're going to focus on ways that we can show that two triangles are congruent to each other, okay? So obviously, if I tell you that I have two triangles and they have the same side lengths and the same angles, you could tell me that those two triangles are congruent to each other. So let me actually pull up Paint here, our favorite thing. Make a little note off to the side. So if I actually, have a triangle, and then I have, let's see if I can do this. I have one triangle, and I make a copy of that triangle. So I have two triangles, and these are two different triangles. Let's say this one is ABC, and this is DEF. Obviously, if I told you that this is 60 degrees, actually that all of these are 60 degrees, because remember, all of our triangles add up to 180, so 60, 60, 60, and this is 60, 60, and 60, and I told you this had a side length of 5, 5, and this would have to be 5, and this has a side length of 5, 5, and 5. Obviously, by looking at these two triangles, you could tell me that they are congruent to each other, right? But we actually, through geometry, are able to, we don't need to know every single angle and every single side in order to be able to say that the two are congruent. So what we're going to talk about in 4.3 and 4.4 are two, we'll start talking about, we'll have a lot, but two postulates that say we don't have to know all the information in order to say that two triangles are congruent. So the first postulate is actually called the side, side, side postulate, or the SSS. Side, side, side. S stands for side, A stands for angle in these postulates, okay? So the side, side, side congruence postulate says we have two triangles, ABC, and looks like we have RST here, okay? So this says that if we have one side, AB, and that's congruent to side RS, okay? And then our second side, which is BC, and you can see the little congruence marks on here. Remember, these mean congruence, is congruent to ST. Okay, ST. And then our third side, CA, I'll make our, is congruent to TR. So we have three sides, and every side is congruent to the other side in the triangle. Then I don't even have to know what the angles are. I can just say that triangle ABC is congruent to triangle RST. So one possible way to show that two triangles are congruent is to show that all three of the sides are congruent to each other. I don't have to know what the angles are. As long as all three sides are congruent to each other, then I can say that the two triangles are congruent to each other. So that's what the side, side, side postulate is. Okay, so we're going to do a couple examples with this. The first one's kind of a proof. Not too hard, though. Okay. All right, so kind of a little proof of, and we're going to use, obviously, our new postulate that we did. So we are given the information that side FJ is congruent to side HJ. So it's actually marked. We have a diagram right here, right? We have a nice little picture. And FJ, this side, is congruent to HJ, which has been marked as congruent on our picture already. Okay, the second piece of information that we're given is right here, which is that G is the midpoint. G is the midpoint of FH. All right, well, by the definition of a midpoint, the midpoint is in the middle of two lines. So if you divide something right down the middle, then your two segments that you have left over are going to be equal to each other or congruent. So we know, based off of just the definition of a midpoint, that these two are congruent. Okay, and we want to prove that triangle FGJ is congruent to triangle HGJ. So we want to basically prove, I'm going to draw it off to the side, that this triangle is congruent to this triangle when it's smushed together. I'm going to prove that those two are congruent. Well, we're going to prove that because we already know that this side is congruent to this side is congruent to this side, and we know that this middle side is actually smushed together. So obviously this third side is congruent to this side. And so if we can show all that, we can use the side postulate to say that these two triangles are congruent. So let's kind of talk through the pieces here, okay? So step one, it is given that FJ is congruent to HJ. Okay, that's our red. We knew that right off the bat. It's given. Got it. Point G is the midpoint of FH. So because point G is the midpoint of FH, we know that, and I'm going to pull this down here so I have a little more room, that FG, line segment FG, is congruent to GH. Okay, and then the last line that we have to deal with is this one right down the middle. We need to make sure that GJ is congruent to each other. Well, GJ is congruent to each other because of the reflexive property. So by the reflexive property, GJ is congruent to GJ. So by the side postulate, or postulate 19, we can say that triangle FGJ is congruent to triangle HGJ. So that's how we're going to use the side postulate. Okay, so let's do a couple more examples. Pretty easy, pretty straightforward, right? Okay, here's a few more examples. All right, so number one, we have triangle JKL is congruent to triangle MKL. So this one's actually going to be really, really similar to what we have before. You'll notice that we have JK and KM are both 8 units. So we could say that JK is congruent to KM. All right, you'll see that JL and LM are both 9. So those are congruent to each other. And then they share one side in common. So obviously those are congruent to each other. Got 3 little lines in there. So now we have the 3 sides of each triangle are congruent to each other. And we can say that, yes, this is true by the side postulate. Side, SSS. All right, so let's look over here. We have triangle RST. Is that congruent to triangle TVW? All right, so this one is actually kind of drawn in a weird way, right? So RST is drawn like this, right? And this side is congruent. These two sides are labeled as congruent. So we're trying to see if it's congruent to TVW. So in this case, T corresponds to R. So T needs to go up here. T, right? And then T goes to V, which goes to W. So you can see between V and W, those are congruent, and between W and T, those are congruent. So we have our triangles kind of lined up here, right? However, we do not actually know if this side and this side are congruent to each other. We don't have enough information to know if those two are congruent to each other. So although we have two sides that are congruent to each other, that doesn't necessarily mean that the third side is congruent to each other. If our angle is slightly different, they might not be congruent. So we cannot prove that these two triangles are congruent just based off of this. Okay. One more example from this section. It's a pretty easy little section. Oops. This is probably going to be the hardest thing, and this is just because we're going to bring back in our distance formula. Okay, so remember that this is our coordinate plane, right? And each of these spots corresponds to a place on our coordinate plane. So what we're trying to do is determine whether triangle PQR is congruent to the other two triangles that are on here. So I'm going to highlight PQR, and we're determining whether or not they're congruent based off of the side. Draw a little bit better. PQR. So we have to basically find the lengths of all the sides of these triangles to see if they're congruent to each other. Okay, so let's start with PQR because we're comparing the other two to that. So the first thing I want to do is find the distance between P and Q. Well, between P and Q is pretty easy because I can actually just count my units, right? Each of these squares represents 1. You can see that right here. So each of these represents 1. So the distance between P and Q is 3 units. I'm just counting the squares there. Okay. The distance between Q and R is 1, 2, 3, 4, 5. So I'm just counting 1, 2, 3, 4, 5. 5 units. Okay. What is the distance between P and R? So I can't actually count that because it's on a diagonal. These are easy because they're straight units, so I count them. Between P and R, I can't actually do, so I'm going to have to use the distance formula. So if you remember the distance formula, distance equals, what we're going to do is we're going to do the change in the x coordinates squared plus the change in the y coordinates squared. And that's how we're going to do the distance formula. All right, so we know that P, point P here is at -1. I'm trying to find the coordinates. It's at -1, -2, -3, and it's at 1, 2, 3, 4, 5. So P is at -3, 5. And R is at 1, 2, 1, 2. R is at 2, 2. So the distance between P is going to be the square root of my change in my x. So my change in my x goes from -3 to 2 squared. And then the change in my y's is going to be 5 minus 2 squared. Sorry for the crazy writing. So -3 minus 2 is -5 squared. 5 minus 2 is 3 squared. And if you do the math on this, you get about 5.83. So the distance from this is 5.83. And you can use a calculator for this. You can simplify it even more, all that kind of good stuff. Okay? All right, so we have the green triangle. Now we have to figure out if any other triangles are actually congruent to it. So let's do RST, because this one looks like an easy one. So we've got RST in purple. The distance between R and S is 1, 2, 3. Okay. That's good. The distance between R and T is 1, 2, 3, 4, 5. All right, so far so good. I have 3 and 3 match up and 5 and 5 match up. Now I have to see if this side over here matches up. And if I can show that this ST over here is 5.83, then all three of my sides are congruent to each other, and therefore the two triangles are congruent. So guess what I get to do again? Distance formula. ST, the distance between S and T. Oh, I have to figure out where S is. S is at 1, 2, 3, 4, 5, 1, 2. S is at 5, 2. And T is at 1, 2, and 2, and then go down -3. So T is at 2, -3. All right, so my change in my X is 5 minus 2 squared. And my change in my Y is 2 minus a -3 squared. And you'll notice if you do this, I'm going to kind of do some math magic here and just kind of skip to it. If you evaluate that, you get 5.83. Ta-da! So now I have 3 sides that are equal to the other 3 sides. So PQR appears to be congruent to SRT because the sides are congruent. So triangle PQR is congruent to, and then we have to match up our sides, right, to SRT because of the side postulate. All right, what about VWR? Is that congruent to these other two? Well, we got to find the length of the side. Oh man, they didn't give us any sides. We have to use the distance formula for all of this. So let's find the distance between V and W down here. Let's find the distance down here, okay? So W is at 0, -3. And V is at -3, -2. Okay, so let's find the distance there. The distance between V and W is the change in x's, so -3 minus 0 squared, plus the change in y's, -2 minus a -3 squared. So we're going to end up with basically 3 squared, -2 minus a -3. 3 squared plus 1 squared. So we are going to end up with a number that is really close to 3, but it's going to be like 3.1 something when I do that work. So I already know because this side is 3.1 something, it doesn't match up with my 3. So wah, 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 the yellow triangle is not congruent to the other 2 triangles. So this is kind of as complicated as it gets as far as side. Again, the idea of side is pretty easy. Sometimes we just have to use the distance formula to find our sides. All right, so a little bit of 4-4. We'll do part of it today and part of it on Monday. Guess what? We have another postulate. But wait, there's more. This postulate also helps us show that 2 triangles are congruent, but we don't have to have all 3 sides the same. This one uses a side, an angle, and a side. Okay, so side, angle, and a side. So first off, we have side RS is congruent to side UV. Okay. Then we have that angle R is congruent to angle U. And last, we have that angle R, or line RT is congruent to line UW. So we don't have three sides are congruent, but we have two sides and the angle that joins them together, which is called the included angle. Those are all congruent to each other. So this is another way. If we have two sides and the angle that matches up those two sides, if we have those are congruent to each other, then we can say that RST is congruent to UVW. Sorry for the crazy W. So another way, we don't have to have every angle and every side congruent to each other. If we have two sides and the angle that connects them, we can also say they're congruent to each other. This is called the side angle side, the SAS, right? So we're going to do one example for that. And then I'll save the other example for class on Monday just to kind of wrap that up. So let's do one just to make sure we get it. All right, so here you go. In the diagram, ABCD is a rectangle. What can you conclude about triangle ABC and triangle CDA? So what can you conclude about triangle ABC and triangle CDA? Okay, well, what do we know? Okay, well, we know that, and I left the answer in here, by the right angles congruence theorem, we know that because B and D are right angles, that B and D are congruent to each other. I want to do another color. So B and D are definitely congruent to each other, right? We also know that opposite sides of a rectangle are congruent. That's the definition of a rectangle. So we know that AB is congruent to DC, and AD is congruent to BC. So we know that those opposite angles are congruent to each other. So because of that, because we have an side, an angle, and another side, we can say that ABC and CDA are congruent by the side, angle, side postulate, by the SAS postulate. And this fill-in should say that opposite sides of a rectangle are congruent. So AD is congruent to BC, and AB is congruent to DC. That's what the fill-in should be right there. Now, obviously, if you guys were kind of paying attention, you could also say that AC is congruent to each other, right, because of the reflexive property, and we could say that they're also congruent because side, side, side. That would also be acceptable, but since we're in the side angle side section, we might as well use side angle side. All right, so that is 4.3, and part of 4.4. We'll wrap up 4.4 on Monday, and hope you guys have a great weekend. Bye.